All right, grade 9, we are starting our new unit, Unit 5 on probability. Now, normally I would teach this unit very slowly, take my time with each concept. However, given the circumstances, we're going to go through this unit a little bit more quickly than I usually do, but do not fear, I'll make sure that I explain everything clearly, and of course you have these videos to rewatch as many times as you need to. So, a couple reminders. First of all, if you haven't already submitted your summative assessment, please make sure you submit it by the deadline or by the deadline that was given to you through email. It's important that you keep that documentation just in case. Some of you owe it to me on Friday and some of you owe it to me on Thursday, but please make sure that you submit your summative assessment when we agreed. Next, so Monday through Wednesday are catch-up days for mathematics. That means for you that beyond this video, you will have one worksheet. And that worksheet is quite long. However, you have the rest of this week and next week to finish the worksheet, as well as to watch the video multiple times because I will just be discussing several concepts. It's a good chance for you to meet with me next week if you are confused on any of these concepts. So please make sure to reach out to me early about meeting to discuss these concepts, and perhaps I can do a Zoom video discussing anything that is causing confusion. But probability tends to be pretty straightforward for most people, and I think that you'll find it relatively easy. All right, so some basic things about probability that you already know from MYP and your studies of probability in grade 6, 7, and 8. So what is probability? Well, probability is a field of study where we describe the chance or likelihood of an event happening. So basically, probability is something that lies between 0 and 1. 0 meaning that the event will not occur at all, it has no chance of occurring, and 1 representing 100% chance of occurring. This means that we can represent probability as a fraction, as a percent, or as a decimal. We call the number that we use to represent the chance of something happening the probability. So it says right here in the blue box, an impossible event has 0% chance. A certain event has 100% chance. All other events can be assigned a probability between 0 and 1. So perhaps a 25% chance or 1/4 of occurring, or a 50% chance or 1/2 of occurring. So you can see this little chart here, this little green horizontal line that discusses the probability. Obviously 0.5 is 50% chance of occurring, meaning that it's just as likely to occur as not to occur. And we've got two types of probability that we're going to be discussing. We've got experimental probability and theoretical probability. Experimental probability is, just like the name suggests, probability that we can calculate after a number of trials have been performed. So what are trials? Well, the number of trials is the total number of times the experiment is repeated. So you try something once, then you try it again, and then you try it again and again. Oftentimes you do this in science class, right? You try things over and over, so you are conducting trials. The outcomes are the different results possible for one trial of the experiment. The frequency of a particular outcome is the number of times that this outcome has occurred. And the relative frequency of an outcome is the frequency of that outcome expressed as a fraction or as a percent of the total number of trials. So that should seem familiar to you. One, because we talked about frequency in statistics, but also relative frequency should sound like how we calculate probability. So for example, I'm going to read this example to you. It says when a small plastic cone was tossed into the air 279 times, which is a lot of times, it fell on its side 183 of those times and on its base 96 times. So the number of trials is 279 times because that's how many times we tossed it into the air. The outcomes are either side or base, so it either landed on its side or landed on its base. And the frequencies of side and base are 183 and 96 respectively, meaning that it landed on its side 183 times and 96 times it landed on its base. The relative frequencies of the side and base are 183 divided by 279. So out of the 279 trials that were conducted, it landed on its side 183 times. And 96 divided by 279. So out of the 279 times that it was tossed into the air, it landed on its base 96 of those times. So what we just calculated there with the relative frequency is the probability. It's a fraction in between 0 and 1, and it represents the chance of occurring through experimentation. So experimental probability is relative frequency. I'm hoping if you haven't done so already that you're following along with your notes. Remember that I have a blank copy of these video lecture notes on the Introduction to Probability section of the Unit 5 tab for probability. So either follow along with the blank notes and create your own notes, or follow along with the key. Okay, so you should be, reading and listening and writing all at the same time. Okay, so let's take a look at sample space. We're going to see some things from set theory that I talked about way back in the day, and so it's a good refresher here. So what is a sample space? A sample space is our universal set of possible outcomes, right? So a sample space is a set of all possible outcomes of an experiment. It's also referred to as a universal set. There are a variety of ways of representing or illustrating sample spaces, including lists, tables, two-dimensional grids, Venn diagrams, and what are called tree diagrams. I'm going to introduce you to tree diagrams today, and we're going to delve more deeply into tree diagrams in a future video. So, if the sample space is simply the universal set, what is a sample space for tossing a coin and rolling a die? Pause the video and see if you can answer this question. So, for tossing a coin, what are the possible outcomes? Either heads or tails. So, how do we represent a set? Well, of course you use those curly brackets. So that's the sample space. It doesn't matter in which order you list the H and T, just as long as you list all of the possible outcomes. What about for rolling a die? Well, the sample space for that are the numbers 1 through 6. 1, 2, 3, 4, 5, and 6. Because there are 6 possibilities when you roll a die. You might land on a 1, you might land on a 4, you might land on a 6. So in this next section, we're going to take a look at some visual ways that you can calculate probability. Well, eventually calculate probability, but at least at this point in time, take a look at a sample space for multiple events occurring. So for example, instead of tossing a single coin, maybe you toss one coin and then another coin, or you toss 2 coins at the same time. So when an experiment involves more than one operation, we can still use listing to illustrate the sample space. However, a grid is often more efficient. So let's take a look at example 2. It says use a 2-dimensional grid to illustrate the possible outcomes when 2 coins are tossed. Well, we could very easily just write the universal set that represents all of the possible outcomes. So go ahead and pause the video and think of all the possible outcomes for tossing 2 coins. Did you come up with this? So you might get 2 heads in a row. You might get a heads first and then a tails. You might get a tails and then a heads. And you might get a tails and then a tails. So we're assuming in this case that we're tossing 1 coin and then we're tossing another coin. So that represents the universal set. Now, often we deal with problems that aren't that easy, so we're going to have to use some other strategies to calculate the probabilities and take a look at the possible outcomes. So one way that we can first look at the possible outcomes in order to calculate the probabilities of events occurring is through a 2-dimensional grid. So a 2-dimensional grid is a grid in which the horizontal axis represents one trial, so that first coin being tossed, and the vertical axis represents the second. So the second coin being tossed. So heads, tails on the first toss, heads, tails on the second toss. Now, what ends up happening if I draw these vertical and horizontal lines is you have these intersections. Well, at these intersections, those are the possible outcomes. So what's one outcome? We read it just like we would a point. So one is heads, heads. Oops, heads, heads. And then another is tails, heads. And then another is heads, tails. And then another is tails, tails. So I've got 4 possible outcomes and 4 intersections represented on the 2-dimensional grid. Another way that we can come up with possible outcomes in an experiment that involves more than one operation is through a tree diagram. And you'll see that tree diagrams are extremely useful for us in the future. So I'm going to toss a heads, and then I'm going to toss a tails. Well, if I land on heads the first time, what are the possible outcomes of the second coin that's tossed? Well, it can either land on heads or it can land on tails. Same thing for this bottom branch. Perhaps I get tails the first time. Well, on the second time that I toss the coin, so I'm tossing 2 coins, remember, one after the other, I could get heads or tails. So how do you read this? Well, you could just look at the branches. Heads, heads, and then heads, tails. So I'm looking at that top branch. And then, of course, I've got tails, heads, and tails, tails. So both of these are strategies that you can use. A tree diagram, so this is a tree diagram, or a 2-dimensional grid, so 2-dimensional grid, to determine the possible outcomes of an experiment that involves more than one operation. Okay? So we haven't actually looked too much at calculating probability yet, but we will get to that in this video. What we just looked at a second ago was just determining the number of outcomes, because obviously we can't calculate probability, which is just that relative frequency of the outcome occurring over the total, without knowing the outcomes, right? So just bear with me there. Now, this is going to reiterate what I talked about with tree diagrams. Illustrate using a tree diagram the possible outcomes when tossing 2 coins. Well, I just discussed that. But what about drawing 2 marbles from a bag containing many red, green, and yellow marbles? How would you demonstrate the possible outcomes? So you're going to draw 2 marbles from a bag. It doesn't tell you how many it contains, but it contains many red, green, and yellow marbles. Pause the video and see if you can come up with a tree diagram that illustrates the situation in example 3b. All right, I don't know if you can hear that, but there are coyotes in the background because I'm in California, and where I'm at, beautiful, but there's coyotes. So back to our regularly scheduled programming here. So we know that, initially we can draw either a red, a green, or a yellow marble. So we're going to go ahead and illustrate that. We can either draw a red, a green, or a yellow marble. Again, we're just looking at possible outcomes. Now, from that bag, if we draw a red, we can either draw another red, or a green, or a yellow. So I'm going to make another set of 3 branches. You can either draw another red, a green, or a yellow. From green, you can draw, guess what? A red, another green, or a yellow. Wow, the coyotes are really singing out there today. So you can draw a red, another green, or a yellow. Now, if you draw a yellow the first time, then again, you can draw a red, a green, or a yellow. Okay? So, what's my universal set, my sample space? Well, I could get a red, and then I could get a red again. So I'm just looking here. I could get a red, and then I could get a red again. I could get a red, and then I could get a green, right? I could get a red, and then I could get a green. So I'm just moving along that branch. I could get a red, and then I could get a green. And then I could get a red, and then a yellow. I could get a green, and then a red. I could get a green, and then another green. I could get a green, and then I could get a yellow. I could get a yellow, then I could get a red. I could get a yellow, then I could get a green. Oops. Erase that. Green. I could get a yellow, and then I could get a yellow. So how many outcomes is that? 1, 2, 3, 4, 5, 6, 7, 8, 9 possible outcomes. Now we're going to come back to we're going to come back to experimental probability later on and actually look at the probabilities rather than just the outcomes. But it's often easiest to first discuss theoretical probability when we actually are determining probabilities. So what is theoretical probability and why is it different than experimental probability? So let's just take a look. I'm going to read through this example. Please follow along on your notes. It says, consider the octagonal spinner alongside. Since the spinner is symmetrical, when it is spun, the arrowhead marker could finish with equal likelihood on each of the sections marked 1 to 8. The likelihood of obtaining the outcome of 4 would be 1 in 8, or 1 over 8, or 12.5%, or 0.125. We did not conduct any trials, meaning we didn't actually spin the spinner a certain amount of times and see that experimental probability of landing on an 8. We just know that, hey, we have this spinner that's partitioned or divided into equal segments, so we can assume that hypothetically you would have about a 12.5% chance of getting a 4, right? That is what's called theoretical probability, right? So experimental probability, obviously you get more and more accurate the more trials that you conduct. But in theoretical probability, it's based on what we theoretically expect to occur. It's a chance of an event occurring in any trial of the experiment. It's, not that it's guaranteed, but it's just based on this partitioning into equal segments, right? So if we're interested in the event of getting a result of 6 or more from one spin of the octagonal spinner above, there are 3 favorable results: 6, 7, or 8, because we want 6 or more out of the 8 possible results. Since each of these is equally likely to occur, the probability of a 6 or more is 3 over 8. Now notice the notation. Just like the statistics unit, notation is really important here. So they put that capital P to represent probability, and in parentheses they put the actual event. So 6 or more. What is the probability of that event occurring? Well, it's 3 out of 8. In general, for an event A containing equally likely possible results, so this is that partitioning into equal sections, the probability of A occurring is the number of members of the event A divided by the total number of possible outcomes. Now you've seen this notation in the set theory unit. The N in front means the number of members. So how many are in event A? Well, if we look at 6 or more, there's 3 members, right? So that's where the 3 comes from. And that N in front of the U for the universal set is the actual number of elements in the universal set. So 1 through 8. So there's 8 of them. So let's look at example 4. A ticket is randomly selected from a basket containing 3 green, 4 yellow, and 5 blue tickets. Determine the probability of getting a green ticket, a green or yellow ticket, an orange ticket, a green, yellow, or blue ticket. So give that a try. So a green ticket. Well, how many green tickets do I have? I have 3 of them. So the problem says that I have 3 tickets. So For A, I've got 3. Now, what's the total number of possible outcomes? Well, there's 12 tickets in total. That's 3 over 12. Now, we're not always going to simplify a fraction when we're completing a problem, but as a final answer, you want to simplify your final result, okay? So, 3 divided by 12 simplifies to 1/4 or 25%, right? Now, what about for B? Now, this is a little bit more tricky. Think about it. A green or a yellow. Well, what's the probability of getting a green? 3 out of 12. What's the probability of getting a yellow? 4 out of 12. Well, we want one or the other, right? So in this case, we're just going to combine their probabilities. Anytime we want a green or a yellow, when we see that word or, we're just going to combine those probabilities. We get 7/12, which we can convert to a decimal or to a percent. So what about an orange ticket? Well, in orange ticket, I don't see any orange tickets. So what's the probability of getting an orange? 0 or 0%. Because it's not actually in the sample space, in that universal set. What about a green, a yellow, or a blue ticket? Well, let's see. What's the probability that I get a green ticket? 3 out of 12. What's the probability that I get a yellow ticket? 4 out of 12. And what's the probability that I get a blue ticket? 5 out of 12. Since I want either a green or a yellow or a blue, I'm going to add all of those corresponding probabilities together. Well, what do you notice? You get 12 out of 12, which is 1. That means that if you were to draw from a basket, obviously you're going to get either a green or a yellow or a blue no matter what. So it makes sense that that's equal to 1 or 100% chance of occurrence. So here we go with the symbolic notation. We are back with that unit 2. So when we're dealing with OR events, we use that union symbol. Remember the union symbol? We have the union symbol and we have the intersection symbol, which we're going to see later on as well. So when we're dealing with OR, we can say the probability of A or B, but oftentimes it's given to you in symbolic notation such as this. Remember that this means OR, one, the other, or both, right? So you simply add both of the probabilities together. Now, they reiterate what I said before, so you can pause the video or stop and look at your notes here about what they're saying about C and D, but I already explained that, so feel free to rewind the video. So in general, we know that the probability of an event occurring is going to be in between 0 and 1, and it's going to include 0 and 1. So you notice that less than or equal to. Well, the reason, of course, is because something may not occur at all, or something may definitely occur, which is equal to 1. So things are going to get a little bit more tricky here. Let's see what you can do. It says an ordinary 6-sided die is rolled once. Determine the chance of getting a 6, not getting a 6, getting a 1 or 2, or not getting a 1 or 2. Remember, this is theoretical probability. We're just tossing it one time, and we're going to see what the probability is of occurring with this die. So go ahead, pause the video, think through these problems, see if you can make sense of some of the more tricky ones, especially B and D. Let's look at A. A is the easiest. What's the probability of getting a 6? Well, in a 6-sided die, what is your universal set, or that sample space? You can either get a 1, a 2, a 3, a 4, a 5, or a 6. Well, the probability of getting a 6 is just one of those, right? So for A, it's just 1 out of 6. Let me do a different color here for B. Well, for B, of not getting a 6, you see that word not. Now that's interesting. Well, we know that we'll either get a 6 or we won't. So we will either get a 6 or we won't get a 6, right? The way we write not is this little apostrophe. So let me erase that, make that a little bit more clear. So of not getting a 6. If you add the probability of getting a 6 and the probability of not getting a 6 together, what do you get? 1, right? Because when you add up something, so you know either you're going to get a 6 or you're not, right? So when you add those two probabilities, the probability of an event occurring and what is called its complement, so of not occurring, it's going to equal 1, right? Because you're either going to get a 6 or you're not going to get a 6. That's guaranteed. You're either going to get 1 or you're not. So you add the two probabilities together and you get 1. Well, how do we figure out not getting a 6? Well, it's just simple algebra. Subtract from 1 the probability of getting a 6. So the complement, the 6 not here, is equal to 1 minus the probability of getting a 6. Well, what is that equal to? Well, that's 1 minus 1 over 6, right? We figured that out in A, the probability of getting a 6, which is 5 over 6. If you didn't understand that, rewind the video and watch this again. All right, let's look at C here. Also, this is annoying me. Let's put that there. Okay, so C says getting a 1 or a 2. Remember, we are dealing with that union, right? So the probability of getting a 1 or a 2, what is that equal to? Well, we're just going to add those probabilities together. The probability of getting a 1 is 1 out of 6. The probability of getting a 2 is a 1 out of 6. Well, together that makes 2 out of 6, or 1/3, right? And you can, of course, convert that to a percent. Okay, if you haven't tried the last one, go ahead and see if you can solve the last one based on how we answered B, the probability of not getting a 1 or a 2. Well, remember that for D, so let me write this down here. For D, whenever we're looking at not, we have to just think of, okay, the fact that if I add the probability of getting a 1 or a 2 with the complement, so the probability of not getting a 1 or a 2, so not getting a 1 or a 2, what do I get? I get 1, right? So just like before, you subtract the probability of getting a 1 or a 2. So in other words, the probability of not getting a 1 or 2 is just 1 minus the probability of getting a 1 or a 2, which is going to be equal to 1 minus 1/3. Where do we get the 1/3? Well, from part C. 1 minus 1/3, it's just 2/3. All right, I hope that makes sense. All right, so the book reiterates what I talked about with complementary events. So they talk about the probability of not getting a 6. Well, you have to understand that when you are rolling a die, you're either going to get a 6 or you're not. So the probability of getting a 6 and not getting a 6, those are complementary events that are occurring, right? It's certain that one of the events will occur, and it's impossible for both of them to occur at the same time. When we add them together, we're not saying that both of them are occurring at the same time. Of course, we're saying that one or the other will occur, which is, again, or means addition, which is why it equals 1 when you find that sum. Okay, now it's going to talk about using grids again. It's just going to make it a little bit more complicated. So let's just read through this and then try the practice problem. Two-dimensional grids can give us an excellent visual display of sample spaces. As we know, we can use them to count favorable outcomes and so calculate probabilities. So before, with experimental probability, we just looked at outcomes. We didn't actually find probabilities, but now we're going to go ahead and use a two-dimensional grid to actually calculate the probabilities after we take a look at the possible outcomes. So they give you that heads and tails example where you toss a coin, which they call coin A, and then you toss another coin, and then they want to know the possible outcomes. So here they say use a two-dimensional grid to illustrate the sample space for tossing a coin and rolling a die simultaneously. So it could either be one after the other or simultaneously here. So you're just doing it at the same time. You're tossing a coin, you're rolling a die, and then they want you to determine the probability of tossing a head, getting a tail and a 5, getting a tail or a 5. That's a little different. So let's take a look here. So go ahead and see if you can use that two-dimensional diagram. draw the two-dimensional diagram first. So pause the video and try that. So did you get this? This is what your two-dimensional grid looks like. So I have 1 through 6 on the horizontal part, and I've got tails and heads on the vertical part. Now that was just the easiest way to label it here for this event. So I noticed that I have 2, 4, 6, 8, 10, 12 intersections that I starred in pink. So that means I have 12 outcomes. So I can either get a heads and then a 1, a heads and then a 2, a heads and then a 3, a heads and then a 4, 5, or 6, heads and then a 6. Or I could toss a tails and get a 1, then a 2, or a tails and a 3, or a tails and a 4, or a tails and a 5, or a tails and a 6, right? So all of those outcomes are possible when I do those things simultaneously in this case. So what's the probability of getting a head? Well, just look here at that horizontal row of heads. There are 6 of them, right? You can see that on the grid. 6 out of how many? So for A, there are 6 out of 12 total, or 1 over 2. So it's 50% likely that you will get a heads. What about getting a tail and a 5? Well, I noticed that there's only one of them here, and I can see that that's true right there as well that I circled. So for B, there's only one time where you have that intersection of tail and 5. So 1 out of 12. What about C? Getting a tail or a 5. So in this case, what's the probability of getting a tail? Well, there are 6, right? 1, 2, 3, 4, 5, 6 opportunities for you to get a tail. So that's 6 out of 12. And then what's the probability of you getting a 5? Well, what would be the case here? Well, we can't say 2 out of 12 because then that would mean that we are doubling up on getting a tail, right? So in this case, we're just adding 1 out of 12. So we could get a heads and a 5, right? So again, there are 2 cases that you can get a 5, but if I add 6 over 12 plus 2 over 12, I am counting tails and a 5 twice because I already counted it here, right? So 6 over 12 plus 1 over 12 is equal to 7 over 12. Okay, I hope that makes sense. All right, our last topic is tables of outcomes. So we've talked about a lot here, which again, that's why I'm giving you the rest of today to really just watch the video. You don't have to start the assignment at all. Just watch it more than once if you have to. So tables of outcomes are tables which compare 2 categorical variables. Remember we talked about categorical data in our statistics unit. We have that categorical data and we've got that numerical data. So they usually result from a survey. So for example, a group of teachers were asked which mode of transport they used to travel to school, and the responses were summarized in the table below. The variables are gender and mode of transport. So they've got gender, male, female, and they've got mode of transport, which is car, bicycle, or bus. So the 13 represents the fact that 13 female teachers catch the bus to go to school. In the following example, we will see how these tables can be used to estimate probabilities. To help us, we extend the table to include totals in each row and column. So you don't see totals right now. So what I'm going to go ahead and ask you to do is we're going to go ahead and extend this. So let's add another row here and another column. So I'm going to add another column as well. So I'm going to find the total amount for each of these. So I'm just going to write in total and total. So go ahead and find that cumulative total for children and adults, and as well as those who liked the ride and those who disliked the ride. So remember, you can have, children and adults both like the ride, or you could just be looking at probability with just the children, including those who liked and disliked the ride. So let's go ahead and fill out that total. So for the number of children, that total amount is 72. So 72. For the number of adults, you've got 58. And altogether, you've got 130 people. So that's that universal set there. And then for the people that liked the ride, you have 83 of the respondents, children and adult, who liked the ride. And out of the children and adults who disliked the ride, you have 47. So what's the probability of the people who liked the ride? Well, that's just going to be your total of all the people that liked the ride, which is 83, out of how many were surveyed, which is 130 people. So that's your probability. And we can go ahead and leave that as a fraction unless, they specify a percent, or it's more easy to interpret as a percent. That's up to you. Is a child and disliked the ride. So the probability that they are a child and disliked the ride. Well, out of 130 total respondents, 17 of them were children who also happened to dislike the ride. Is an adult or disliked the ride. So is an adult or disliked the ride. So take a moment to try and figure that one out. Well, here is an adult. What's the probability that they are an adult? Well, you have 28 plus 30. What about the probability that they disliked the ride? Well, you'd have 17 plus 30, but we've already counted the 30, so we don't want to count it more than once. So really, it's just 28 plus 30, so that's the probability that they are an adult, plus 17, which is the probability that they disliked it and were a child, right? Because it's or disliked the ride. That includes children or adults out of the total, which is 130. Well, if you add 28 plus 30 plus 17, you get 75. All right. So that was C. D. Liked the ride given that he or she is a child. So we already know that they're a child. So what's the probability that they are a child and they liked the ride? That's what that's saying. So they are a child who happened to like the ride. Is 55 of them. So, right, 55 of those children like the ride out of 130 total. Or sorry, not 130. Out of 72. Because we're just looking at children, right? They like the ride given that he or she is a child. So we are just looking at children. That given is looking at what's known as conditional probability, which can get very tricky here. So the condition is that they are a child. So we are just looking at the frequency, that total frequency for just children, which is 72. And out of those 72, 55 of those children liked the ride. Okay, is an adult given that he or she disliked the ride. So, okay, given that he or she disliked the ride means we're only looking at the people who disliked the ride. So that's 47. Well, how many of those 47 were adults? Well, 30 of them. So that's where that comes into play. And all of those fractions represent individual probabilities for all of those separate events. So again, some things before I go here. Remember the notation? So for A, for example, if we're going to say the probability that they liked the ride, we would say that capital P, that they liked the ride. That's the probability that they liked the ride. And that's going to be equal to 83 over 30. So watch this video again. Take good notes. That's your homework for today. Watch the video as many times as you need to. Take good notes. Make sure you understand everything. If you have questions, since we're not going to have anything new next week from Monday through Wednesday, it's your opportunity to reach out to me if you need help. I hope you have a great day, and I hope you have a wonderful spring break. I think we all need it.